Hello everyone, welcome back to Act of Learning. Consider three circles that are mutually and externally tangent to each other. Given such a configuration, we can always draw two new circles. A circumscribing circle that is internally tangent to all the three circles, and an inscribed circle that is externally tangent to all the three circles. The question that we are interested in this video is about the distance between the centers of these two circles. To answer this question, we first need the radius of the two new circles we created. An explicit formula for these radius is given by a really beautiful theorem in geometry. If you know what that theorem is, share it with us in the comment section below. It says, if there are four mutually tangent circles, then the radius of these circles satisfy a quadratic expression shown here. Solving it in terms of the radii of the fourth circle, we can see that there are, in general, two solutions which correspond to the radii of the two new circles. Quite simply, we were given three mutually tangent circles. We created two new circles and found their radius with an explicit formula. We are now interested in the distance between the centers of the newly created circles in terms of their radius. Considering that our problem involves a lot of circles, it should come as no surprise that we use circle inversion to solve this problem. We already introduced and proved the basic properties of inversion in the video about Pappus chain in our channel. I'll leave a link to that video in the description in case you haven't seen it yet. For now, let's review some of the properties of inversion. Let O be the center of our inversion circle and R be its radius. Then the inverse of a point A with respect to this circle is a point A dash such that OA times OA dash equals R square and A dash lies in the ray OA. Inverse of a line passing through the center of inversion is the same line. It doesn't change. Inverse of a line not passing through the center of inversion will always be a circle passing through the center of inversion. Inverse of a circle not passing through the center of inversion is a circle not passing through the center of inversion. Circles orthogonal to the inversion circle remain invariant under inversion. Finally, the angle through which two curves intersect does not change under inversion. This property is very useful because it tells us that the number of intersection points and tangency points remain the same under inversion. That is a lot of information. So now is probably a right time to pause the video and take a closer look at these properties. Quite amazingly, all of these properties can be proved with just basic geometry. You can always visit the Pappus chain video where we have proved all this. Before proceeding with the solution, we revisit something very important. We can easily see that circle inversion alters the distance between any two points. This variation in distance can be quantified using the idea of similar triangles. Simply put, the distance between points A and B before and after inversion can be related by the expression A dash B dash equals AB times R square by OA times OB. One of the key properties that makes inversion such a powerful tool is the idea of cross ratio. Given any 4 points W, X, Y and Z, the cross ratio is defined as the product of the ratios Wx by Wy and Yz by Xz. This is usually denoted by the Greek letter lambda. We can prove its invariance easily using the expression we had for the distance between 2 points. Just make the usual substitutions and a bunch of cancellations later, the equality becomes apparent. Consider these 4 points in our problem. Let capital R be the radius of the circumscribing circle, small r be the radius of the inscribed circle, and d be the distance between their centers. Now the cross ratio between these points can be expressed in terms of the radii of these quantities quite easily. The terms in the cross ratio are obvious from the geometry of the circles, and we arrive at this expression for the cross ratio. Our plan to solve the problem now is to make a clever choice of inversion and use the invariance of cross ratio to simplify the problem considerably. We begin by constructing a circle that is simultaneously orthogonal and collinear to both the circles. By orthogonal, we mean the brown circle intersects the circumscribing and the inscribed circles at right angles. Here's a small challenge. Can you see how we can find a circle simultaneously orthogonal to two given circles? If you can, share it with us in the comment section below. Now take this point, the point of intersection between the orthogonal circle and the line of centers, as the center of inversion with some arbitrary radius of inversion. The radius of inversion actually is irrelevant, as can be seen shortly. Let's see what happens to our setup with this choice of inversion. The line of centers passes through the center of inversion, so it remains invariant. The orthogonal circle passes through the center of inversion and is perpendicular to the line of centers. Its inverse then becomes a straight line perpendicular to the line of centers. The yellow circle is perpendicular to both the orthogonal circle and the line of centers. Hence, its inverse, which is a circle, will also be perpendicular to both the line of centers and the orthogonal line. That is only possible when the inverse of the yellow circle is symmetrical to both these lines. The same applies for the other circle as well. Thus, because of our choice of inversion, the inverses of the circumscribing and inscribed circles become concentric. It is also not difficult to see that the three given circles invert into equal mutually tangent circles. If we now let capital R dash be the radius of the outer yellow circle and small r dash be the radius of the inner purple circle, then the cross ratio of the 4 points after inversion becomes r dash minus r dash divided by r dash plus r dash the whole squared. With some simple geometry, this ratio can easily be calculated as 3 by 4. Because the cross ratio does not change with circle inversion, we see that our expression for the cross ratio equals 3 by 4. This simplifies nicely to d square equals capital R square plus small r square minus 14 times capital R times small r, which gives the distance between the centers of the circles in terms of their radius. Hope you enjoyed the discussion and see you in the next video.